Hello friends. Here is a question that seems simple at first. What is the slope of a line? Easy. Rise over run. Take any 2 points, subtract the y values, divide by the difference in x values, and you are done. The slope is the same everywhere on that line. But now look at a curve, like y equals x squared. The slope here is not constant. At x equals 0, the curve is perfectly flat. At x equals 3, it is steep. Every single point has its own slope. So how do we measure something that keeps changing? That is exactly the problem calculus was built to solve, and in this video we are going to walk through the beautiful idea that makes it work. Alright, let us build the first piece of our solution, the secant line. A secant line is simply a straight line that connects 2 distinct points on a curve. Take y equals x squared. Pick point P1 at x equals 1, where y equals 1, and point P2 at x equals 3, where y equals 9. Draw a straight line through both. The slope of that secant line is y2 minus y1, divided by x2 minus x1. That gives us 9 minus 1, divided by 3 minus 1, which equals 8 divided by 2, which equals 4. This slope of 4 is the average rate of change of the function across that interval. It does not tell us the slope at any one point, but it gets us close. Up next, we sharpen that idea into something exact. Now let us meet the tangent line. Where the secant line cuts across a curve between 2 points, the tangent line skims the curve at one precise location. It touches the curve at exactly 1 point, and mirrors the curve's direction at that point. The slope of that tangent line is what we call the instantaneous rate of change. It tells you exactly how fast the function is changing at that single point, not over an interval, but at a precise moment. Think of a car's speedometer. It does not show your average speed over an hour. It shows your speed right now. That is instantaneous rate of change. The tangent line captures that exact idea geometrically. So the big question becomes, how do we actually calculate that slope? The answer is the limit, and that is exactly where we are headed next. Here is the core idea that bridges everything. Take your secant line through P1 and P2. Now slide P2 closer and closer to P1 along the curve. As that gap, which we call delta x, shrinks towards 0, something remarkable happens. The secant line gradually rotates and settles into the tangent line. The slope formula becomes the limit, as delta x approaches 0, of f of x plus delta x minus f of x, all divided by delta x. That expression is the formal definition of the derivative. We are not dividing by 0. We are asking, what value does this ratio approach as delta x gets infinitely small? The limit gives us that exact value. Secant becomes tangent, average becomes instantaneous, and algebra becomes calculus. Let us now apply this to a real function and watch the numbers work out. Let me show you this working on a real example. Take f of x equals x squared and find the derivative at x equals 1. Plug into our limit formula. F of 1 plus delta x minus f of 1, all divided by delta x. Expand the top. 1 plus delta x squared gives 1 plus 2 times delta x plus delta x squared. Subtract f of 1, which is 1. The numerator becomes 2 times delta x plus delta x squared. Divide every term by delta x, and you get 2 plus delta x. Now take the limit as delta x approaches 0. The delta x term vanishes, and you are left with exactly 2. The slope of y equals x squared at x equals 1 is 2. That is the derivative. Clean, exact, no approximation. This same process powers tools you use every day, and that is what we look at on the final slide. Alright, so why does any of this matter beyond the classroom? In machine learning, every neural network is trained using gradient descent. The model has a loss function that measures its error. The derivative tells the algorithm which direction to adjust the model's weights to reduce that error. Without derivatives, there is no training. In robotics, a robot knows its position at each moment in time. The first derivative of position gives velocity. The second derivative gives acceleration. Every motion controller runs on this math. The derivative is the engine behind both artificial intelligence and physical machines. We started with rise over run on a straight line, moved to the limit definition, worked through the algebra for x squared, and arrived at the derivative of 2. That one idea connects it all. Thanks for watching Webronaq.